All right, so let's get started. Last but not least, for all the things, technical things that we have heard, we still need good sort of a yield and reliability sort of a management in order to really get the die cost down and also to ramp up quickly in volume production. As Bruce also mentioned in the morning that any time you lost in the ramp stage actually means your revenue and profit loss. So anyway, so the final session here is entitled The Yield and Reliability Challenges for the Deep Submicron Era. And the lecture will be delivered by PK Mozumdar. He's currently VP of Integration Practice at PDF Solutions Incorporated. He has been doing this for quite some time, quite a few years, dealing with the technology yield ramp aspects all over the world. And before this, he was with TI for some time, looking at technology options, process flow, design for manufacturing, process control. So with a lot of experience in the yield improvement. So let's welcome PK.
Yeah, I can use the pen. So my job today, first of all, before I start with what my job is, I should say that it's a privilege and honor to be standing here in this forum and talking about the challenges for the next few decades. And my job, as I was starting to say, is to make sure or ensure that all the advances that you've talked about so far actually do work and the red brick wall doesn't hit us early enough. So what I'm trying to talk to you about today is the insurance for making sure that the advances that you make here actually do work in manufacturing. And the gains that have been talked about earlier in the day don't come back and bite us because we don't make the yield ramp and the reliability. And Bruce Son from Intel has mentioned a little bit of that. We heard a little bit of that from TSMC. So I will just give you a flavor of essentially what the yield and reliability challenges are today. What are some of the sources of this yield and reliability loss that's going to put us back if we don't solve these problems quickly? Some of the integrated techniques and tools for yield improvement. Talk about characterization of a process or the process design interaction to be precise. Talk about some of the monitoring aspects and the improvement aspects. Talk about functional yield loss, parametric yield loss, and a combination of them together. I'll be addressing a little bit of designing for yield that actually Jack mentioned early in the morning during his introduction. And finally, I'll touch on the reliability portion. Now, I have two advantages, one of which is, and then Kobayashi-san talked about the physics of the reliability aspect, so I can now spend a little more time talking about how you design for the reliability itself, just like you design for yield, essentially. So with that, I'm going to get started through. And we have all looked at the manufacturing technology roadmap, and we are pretty clear that this is accelerating. So what does that mean for us? It means the gap between the design and manufacturing is actually increasing, and we have less time within silicon to make up that gap. That means things have to be done almost pre-silicon or outside the silicon in order for you to be able to make this accelerated roadmap. The product market windows are narrowing, which means yield ramp is important. It's not just the final yield that you get to, it's how fast you get to it and how quickly you can make sure that there are no delays, because any delay on the ramp is going to cost you a lot of money, and I'll talk about that at the end. And then we have systems on a chip. That is, we have all different kinds of functionality on a single chip, and with the 300 millimeter with the die size, you can see, you can put in more and more functionality on the chip. And again, this was talked about earlier in the morning where people want more technology, so more functionality on the chip. This means that you need a very comprehensive characterization of the design process interaction up front, and you have to do a very complex process optimization. And all this has to happen together. And there are these pushes from three different directions of the design manufacturing gap, increased time pressure, and increased manufacturing complexity. And you got to do all these things with the minimum amount of silicon. So if I go through, I'm going to underscore this by a very simple graph that we had seen before, which is if you look at the amount of time for a certain part to get to 1 million units, if you look at your cable TV or color TV, it was in the order of 10 to 15 years before you saw 1 million units from production. What you see today in the PlayStation is less than a week, it's actually a few days. That underscores how quickly you need to get things into the market, how quickly you need to ramp yield. So it's not good enough to have great processes, great designs, you've got to make them work together. And that's what this talk's all about, really. This fact is just a reduction from this graph. Essentially, it says, as you scale down the technology, you've got to ramp real fast. You've got to get larger number of wafers quick. So what are the integration challenges? We have talked about this throughout the day again. Time's limited, takes more money to bring things into production, and the technology is getting more and more complex. You have new processes and new materials, and this is going to cause you more fun as you continue along. So one of the things I should have mentioned, which I did not, I'm sorry, is that I have about 84 foils, if you look through the books. I'm not going to go over all of them. I did it for completeness' sake because this is kind of a new topic in IEDM. So at certain points, I'm going to skip through foils based on what's going on, and this is one of the points. Please skip through about 3 foils, and you should be able to see this one. And I apologize for doing that, but that was the only way we could go through a sensible amount in this 1 hour. So if you look at the situation, deep submicron design will require extremely low fail rates. This is obvious. That is, you put more and more into a single die, that means you can tolerate less and less fail rate. That means you have to characterize the feature failure rates, and this is a very, very significant task. If you go back and look at what 300 millimeter does for you, it accelerates the ramp in the design complexity. That means your design is getting more complex, you're putting more on the chip, which means that you need to make sure that you get record failure rates within parts per billions of contact and via failure rates. Think of a contact via stack, that's got to be in part per billion. Your defect densities have to be in 0.1, 0.2 defects per centimeter square. And you've got to characterize this pretty quickly, because if you cannot, you're not going to ramp that yield. And the next generation process, as you have seen, have new materials, which means unforeseen process and design interactions. All this means that you're going to need new techniques and new tools to ramp your yield. And that's what we're going to talk about. Let me take a little bit closer look at the escalating complexity. If you look at going from 0.35 to 0.13 micron, you can very easily see that the number of transistors have gone about 8 times, essentially, twice per generation or 2x per generation. This is well known in this IEDM forum. What you also see is that you get much larger than 8x or slightly larger than 8x number of increase in your contacts and vias. I call them features essentially, and you'll see why I'm calling them features and not just straight contact and via. Because when we talk about this in more detail, it will become obvious that it's not just the number of contacts and via, the number of holes that you have in your interconnect. It matters how they're placed within the design and what environment they're seeing. And that's a big, big problem for a systematic portion for the yield, which I'll come to. And then finally, we're getting new materials, which I talked about. This is actually a very interesting graph. If you look at the blue portion, what it talks about is that if you look at the traditional defect density, your yield should have behaved somewhat like this. It should have flattened out. With the increase in the number of interconnect layers, you're going to get some reduction, but it should have flattened out. What you're seeing instead is the red curve. This gap between the blue curve and the red curve is the design to silicon yield gap. This is the systematic problem that comes about because of these feature changes. The number of features have increased, they're coming in different environments within your design, and you're seeing this huge gap. This is the process design interaction that we'll be talking about today a lot. And this is the systematic portion that absolutely kills the early yield ramp. So characterization of this, making sure that this doesn't happen, your red gets closer to blue, is what yield ramp's all about. So the first thing that we need to talk about is how much of this is bothering you in number of dollars. If you look at it back from 0.35 to 0.18, 30% of the loss is coming due to the process design interaction, the feature-based yield loss. Okay? The good news is that you can almost recover all of it. And that's the good news that we're going to talk about, because you really don't want to hear about how close the red brick wall has gotten. You want to hear about how far we can push it. So that's what we're going to be talking about, how to get rid of this design manufacturing interaction, because this is the one that's blowing the yield ramp. So the solutions that we have to create for today's technology in order to make sure that you make those yield numbers and the yield ramp, first thing you have to change the way you characterize process design interactions. We talked about it. New materials, less amount of time. That means you got to choose a new thing. You cannot look at yield as an afterthought. I know we are in the last presentation, but frankly, what I want to convince you about today is that this is one of the items that you have to look at even before you have completed your process and your design is still in software. It hasn't even taped out. Got to look at this interaction. That's key. Because as you'll find out, the game is lost if you're at qualification and you find out you have systematic yield problems. You're not going to make it. That's what takes the best of breed to do. Make sure that before even you qualify, you have this all characterized. You have to characterize the manufacturability to subparts per billion. This is something we talked about. We can look at numbers later on. But this, believe me, this is where you have to get to. To get to the yield numbers that will support that increased productivity and the the cost benefit that you can get. The cost benefit that was talked about today was the production cost. This makes sure that that translates into cost of goods sold. That's a key difference. And the difference comes from this, making sure you get subparts per billion. In order to do these, you have to apply some new tools and technologies that takes this integration information throughout the development flow. That is, you got to bring back designing for yield, both in process and during design or layout, early into the process. You cannot wait for it if you want to make sure you're ramping yield correctly. And you have to accurately simulate manufacturability, reliability, and yield before even production begins. So this is a significant challenge for us today. So the way I'm going to go through the rest of the talk is I'm going to talk about some of the sources of yield and reliability loss, talk about the characterization and monitoring. How do you do this characterization early on? I'll take some very specific examples on parametric yield loss, because what is happening is that we are finding out more and more that things are no longer simple digital. You have system on a chip, and even digital parts like SRAM show parametric yield loss, more than catastrophic. And you'll see why. And then I'll talk about designing for yield, which is becoming a really important issue, especially with the schism between fabless and foundry. This becomes a huge issue for us. Happens even to the IDMs. Finally, I'll touch on the reliability a little bit, talk about the simulation and optimization. And finally, I'll summarize with the yield learning, showing you what kind of learning curves people see today, what it means in terms of money. So if I look at process-related yield loss as well, you have misprocessing, which we talked about. We talked about process control, how to run a bay, etc. There are systematic defects and random defect portions out of it. I'll talk about both of these a little bit, talk about the systematic more, because people here understand the random defect pretty well. Talk about design marginalities when an IC is not robust enough, that it fails due to the smallest variation on your process. And then we'll talk about the reliability, which is the front end and the back end portion. Talk about NBTI here, which is a big issue. And then some of the things that Kobayashi-san has already talked about, I'll touch on it very briefly. So if you look at the yield loss mechanisms, let me take the right-hand portion first, the random part. One is contamination. This is just dirt. This is created by combination of wafers, equipment, PM cycles tend to change that. You have clean cycles, etc. So that's something that you have as contamination. There are assignable causes. For example, you get clustered defects. You can get scratches during CMP, etc. Those are assignable causes. You see them constantly happening too. Today, I'm not going to spend a whole lot of time on this. And it's, I was thinking about it towards the end and talking to Jack that nobody talked about essentially how do you physically measure the defects, the inspection equipment. But I will not have the time to go over that. But that's a key issue in its own right. What I'll be looking at more is the systematic portion. what is the process-related yield loss, essentially. For example, your device is too leaky, or it doesn't have enough drive, can't drive the circuits, can't drive the back end, for example. We talked a lot about front end today, how you create new transistors, etc. That's got to drive this whole 6, 7, 8 layers of back end. It has to go through narrow vias, through barrier layers, etc. So that's one of the things. Second part is the design. That is, you make your design so sensitive to the process that it fails. Really what the big important part of these two is that the process design mismatch. That is, you have a process that when you introduce the design to it, there's a mismatch between those two. And it'll become clear when I talk about it a little more what that mismatch really is. Okay? And that's really the key to making sure that you get yield. As I said, I'll talk very little about it. We've always been doing random defect characterization. We often go and look at impact of defects on yield. You have different vendors providing you tools. You can look at the defects. You know that there are kill ratios. Things impact yield. However, what we are finding out, and it's been talked about earlier, is because of the metal densities, the poly density, etc., the layer densities and the critical area of layers, that you have to characterize this defect size distribution and the spatial location of the defects pretty accurately so that you can actually go back and see what you need to do with the defects. How do you get rid of them? So you have to first of all characterize this to find out what your impact on yield is. For example, if your critical area is such that the defects below this do not impact you, no point working on them. However, the next generation, they will become important. The spatial density tells you about the footprint of the equipment, where it is coming from, etc. So it's very important to know both the spatial as well as the size density. Again, it's very important to mention here that as we go backwards, that is, as we go into the regime where the smaller and smaller defects impact you more, it's becoming tougher and tougher for the inspection equipment to physically measure and accurately characterize them. And the kill ratios, that is the correlation between a fault or a failure to the physical defect that you observe, becomes worse and worse. So you often have to resort to electrical defect characterization. And when we talk about the test chips or the characterization monitors, I will show you the kinds of structures that you require in order to make sure that you're electrically characterizing the defect density, which correlates pretty well with the faults. So I'm going to jump through one more foil, and I'm going to talk about the manufacturing variation. This is where we talk about a CMP, or essentially an ILD polish, for example. After the CMP is done, you obviously see some across wafer effect. But what has come out now, or what is more stunning over the last 5 years or so, is that the intra-die variation, that is the feature-dependent variation on the die of how much ILD remains, actually is more significant than what is across the wafer. So what has now become a truth is that the intra-die variation, which is based on the features that you see at the bottom of the ILD, that is the density of, for example, the poly or the metal, is more important to the non-uniformity than across wafer variations. And this will become evident when I talk few foils later about what this means for us in terms of a design process interaction. I'm going to reorder the foils a little bit here and talk about something that you obviously know very well, which is examples of where you have to make improvements in the process. I'll first talk about Salicide, which has always troubled us. Talk about some aspects of it. Then I'm going to talk about via, and here I want to introduce the concept of a feature. What does it mean to say that my via has 5 parts per billion fail? Which means that if I have a layer of via with 6 million vias on it, I can see a 95% yield. What does it mean? And we're going to talk about that a little bit. I'm going to leave out the process-induced damage, not because of anything else, but because of lack of time. However, this is a very, very interesting concept where you have a relation between equipment, process, and the features or the design that you look at. But unfortunately, I will be leaving this out today, going through the other portions. So Salicide integration issues. You all know about the junction leakage, contact resistance, that is quality of the salicide on which the contact falls, especially if you're talking about borderless contacts. Stringers that you can see along possibly STI borders. And of course, the salicide ruptures on the N plus P plus transition. People thought that this had disappeared with trisilicide. Well, guess what? It came back with narrower lines. Because as the line becomes narrow, it becomes more evident that there are stringers. If there's a wide line, then the probability that you'll send your electrons across will be much, much better. So this has come back again. So I'll talk about the rupture a little bit. Here is a case, you can see that the salicide along the N plus P plus transition on an SRAM, which you often see on the poly having N plus P plus transitions, is actually rupturing. It's becoming thinner. You can see some stringers. Certain areas may not have good salicide. There are two aspects of this, very interestingly. First thing is just the resistance in this direction is a problem. Second problem is on this butted transition, if you drop a contact, that contact resistance increases. And guess what? That makes your SRAM fail performance. So this is a very key aspect of salicide integration. Here is a simple example of the green line showing where the salicide worked well for an SRAM, red line where it didn't. Simple case, all of you know it very well. You are able to measure this red line, say, problem with my salicide, look at the NP transitions. You often look at the contact resistance on the butted transitions. You figure out what to do with your salicide. You, of course, can change your salicide conditions in the process. Some people even go ahead and widen the salicide a little bit, a polyline. You may not be able to do this in an SRAM because SRAM, the situation is tight. You have a tight layout, compact. However, you may be able to do it in a logic block where you have a long line with butted transitions. You may be able to widen it. So there are two ways to skin this cat. One is to fix the process. The other is to actually do something to the design itself. And we'll come back to this theme again and again. If I look at a via, I'm looking at essentially a stack here. What you're looking at is some amount of coring, some amount of misalignment, and hence printing islands, etc., which causes problems in your stack. This is the same thing that you see in SRAMs too. What we are looking at is a sort of an yield plot, which says that yield's reasonable here, but as you move towards the freezing zones or the blue zones, top left, you see issues. This is probably coming because there is misalignment along that edge, or maybe there was a problem in the edge, a gas flow in the chamber, which caused that. The reason you need these kinds of graphs is because it gives you a footprint of what is going on. It gives you a clue to what piece of equipment you should be looking at or what conditions should you be looking at. Okay? What is more interesting is a graph like this. Consider a fact called loading. Loading is just inverse of essentially pitch. That is how densely are the vias packed. And if you look at the resistance, what you will find is that it should have behaved in a linear fashion in a via chain. It doesn't. It gets super linear. This is not surprising to you again because there are photo and etch loading effects that you are seeing, essentially. What is important though is you have to characterize this pretty well. Because if you do not characterize this well, and if you look at vias having great resistance here, and you don't have chains with high amount of loading, you're not going to pick up the problem. And guess what? If your product has a bunch of vias in this regime, you're in trouble. If not a catastrophic fail, you can see parametric fails at least. Okay? The second important thing here is that you must have your test structure or the characterization structure that has different kinds of vias under different layout conditions. If you do not do this, if you just look at your scribe line structures, you will not be able to pick up this change in linearity, change in slope. Second important thing is, it also drives for you what kind of process capability you must have in place. We talked a lot about process control, we talked about having good CPKs, etc., but on what? You don't need CPKs for everything, you don't need to tighten everything. It's going to take too long, it's going to cost too much money. What you want to do is, you want to make sure that if you have a bunch of vias with this kind of loading on your product, then that's the curve you want to look at here and make sure you know how much misalignment tolerance you can tolerate. So generating tolerances for your process and figuring out how well you need to control process, how well you need to design them, results from good characterization and understanding how the chains that you're talking about, how they appear in your product set. And got to remember, this has to happen before the product hits the process. If it's hit the process, you have a yield crash, too late for a yield ramp. I want to go back to the issue of the intra-die variation. I'm sorry, I'm moving a little backward and forward here. I will try not do that anymore. Actually, I won't do that anymore. Here is the case where we are looking at essentially the ILD variation. We all know very well that putting in dummy fill is a great way to get rid of it. Because really this intra-die variation is what underlying feature density difference are you seeing. The CMP is sensitive to it, so you'll see basically more areas where there's less density, etc. One of the ways to deal with this is a dummy fill. But guess what? If you do the dummy fill, you have now introduced all these extra capacitances. And for all of us who do mixed signal, this is a killer. So it's very, very important for us to understand how any change in the process that we are making, by let's say layout, has a direct impact on your performance on the product. This is the interaction that is what systematic yield is all about. This is not due to contamination. This is because your layout has a different interaction with the process depending on how the layout works, what kind of features the design has. So what I then want to go to is talk about the integrated design process method of actually getting to the yield ramp. So first things first, a little bit of motivation. I've been talking about this, so it shouldn't take too much time. We have been doing traditionally design, process, and manufacturing in isolation. We bring them together and find out how things work. We go into a huge debug loop. What I've talked about so far says that we go to look at an integrated solution. That's absolutely key. How does this work? Essentially, you need to make sure that your process is characterized fairly well. You have a good understanding of the features that go into design. Realize I'm not talking about a taped out design yet. And I'll briefly go over that a little more. I'm talking about what features does your design have. Does it have isolated vias which fail a lot? Do you have long runner lines in poly where salicide break is going to be an issue? How is your SRAM going to be laid out? That kind of things. You have library components, you have SRAMs that you run early on. You can even look at shrinks from your previous generation to see where the trouble hotspots are going to be. What you need to do is you need to take those design elements and those process elements, combine them in a way so that you can characterize the interactions between them. And we talked about a couple of them a little bit early. And then go back and solve the design and the process problem in a constrained way so that you don't kill each other. That is, one does not fight against the other. This is the key component to making sure that you don't get systematic yield loss. So how do you do this? You need to spend a little bit of time on this foil, not to worry about the yield model or the equation. Actually, that's almost immaterial to the problem that we are dealing with. What is important here is to figure out how the design and process interact. For example, here is a case where we are looking at layer yields. We are saying, what kind of yield should I be seeing in the product due to the poly layer? Well, 0.99. That's nice. Shouldn't be a problem. But I go back to the vias and I look at different kinds of vias. For example, bordered versus borderless. And again, this audience, it's really preaching to the choir, but you can immediately see that the borderless vias are an issue. The question is, should I then jump ahead and go ahead and fix borderless vias? Depends. First thing it depends on is, do I have any of them in my product at all? So what I have to do is an attribute or layout attribute extraction. How many vias do I have which are bordered? How many vias do I have which are not bordered? If there are only a few thousand of the borderless vias, maybe I can get away with it. This is not the case. Here it's showing that there's 20 parts per billion fault, and there's enough number of borderless vias that I do see a significant yield loss. We're talking about a single layer of via giving a 10% yield loss right off the bat. Okay? If this was not an issue, that is, if I didn't have enough vias out here, this would have shown up to be 0.99 or 1.0, then it's not a problem. Yes, borderless vias are not great, but you know what? For this product, it's fine. So this drives the focus or the Pareto by which you should be fixing problems. Second part is that how do I make sure that I understand that the layout attributes that I did extract, I have a reasonable understanding how they're going to behave when I introduce this product into the process line. And there comes the test chips. I want to go back and say these are not traditional test chips. We have to be very careful how you design these test chips. And I talked about it during the VIA. I'm going to call them characterization monitors. because these are monitors that let you characterize the design process interaction. This is not looking at a via chain of 100,000 vias and saying, I'm good, 99%. It's making sure that you have chains which have enough statistics in it, that is, you have long enough chains so that you can get to these subparts per billion level. Also, you must have it under different neighborhoods. We talked about one little bit, which was essentially having different pitch or loading. You could have simple things, a via around metal, with metal around it. Whether you have metal 1 or metal 2, that is the upper layer or the lower layer, is totally going to change your failure rate. So characterization monitors are the second key portion. You got to take and put these two together into this kind of a matrix to find out where your hotspots are early on and work on those problems along the Pareto of the yield. That's really the key to defeating the systematic yield. I'm going to take a foil that is not in your handout. I said I'm not going to go back, but I didn't say that I'm not going to take some which is outside. So here is a case where we're looking at different via configurations. Essentially what we are doing is we have cases where we have banked via, we have vias which are at one edge, isolated along different metal layers, for example, the upper and the lower. And what we can do is we can take an attribute extraction from the product. That is, you can look at the product, you can count the types of vias that are banked, for example, count that are ISO, and then you are able to convolve it with this characteristic. This characteristic is actually fairly interesting and important. What it essentially says is, as the loading factor or as the pitch increases, your failure rate increases too. That means you yield lower and lower. What is also important is it's in the environment that it's at. That is it isolated? Does it have more neighborhood of metal on the top layer, more neighborhood of metal on the bottom layer, because the photo is going to change, the edge conditions are going to change, and they're all going to impact you differently with respect to the yield. This characterization, which we call lambda here by a single term, is essentially the essence of the process design interaction, figuring out how different attributes of the design or different features interact with the process that you have. Oh, something weird. Okay. I'm sorry. Back to where we are. Here is a case where we're looking at two different products. It's just to exemplify what we talked about a little bit earlier. Essentially, you have design A and design B. Both of them should be yielding really well with respect to defectivity. But you can see here is product B. I should have said product B instead of block B, which has a huge systematic problems, probably with the borderless vias. It's very, very important that we be able to model the difference in yield from different products before you introduce it into your technology. And the key to that is what I talked about a little bit back, which is doing the characterization and making sure you extract all the attributes that come out of it. Next thing I want to talk about is really a little bit about the characterization process itself. Here's a graph that was shown by Miyamoto at IEDM 2000, where he talked about the defect density, that this is the effective D0 of the product, essentially. Going down the blue curve, and how the monitor, which was an SRAM, was always over-predicting the yield or under-predicting the D0. There are two components in this. One is that simple structures like SRAM are not enough. And secondly, there can be large differences from simple things like parametric variations, which I will talk about in a little more detail, because there's a lot of it that we are seeing which are coming up as analog or mixed signal rather than pure digital parts. So this parametric variation or this parametric difference is a huge issue. The same paper, Miyamoto goes on to describe what kinds of characterization monitors or test chips are used in order to make sure you are able to track the blue line instead of the red. You can see there are SRAMs. There are some high density SRAMs. What you also notice is number of nests which get you the electrical defect size density. This takes up a lot of area to give you statistical validity, but this is really, really key. We talked about, or we touched about very briefly on the defect density and characterizing it correctly, and the electrical defect density. These are those structures. You also have structures which are Kelvin, snakes and combs, etc. You have conditions with bordered combs. All these are doing is these are telling you what kind of difference you will see under different neighborhoods or different attributes on your product. So this is the case where you'll be having vias with different chains, etc. You also have device and process with different neighborhoods. For example, as I talked about in vias, or in device, for example, your NMOS, under different conditions or different densities, is going to behave differently. You know that. Your isolation is going to behave differently, your on current is going to behave differently. In fact, there are a bunch of manufacturability rules that you always have, or extended rules that you have to make sure that you don't get into these neighborhood problems. This is the kind of test structures or the characterization monitors that you have to put in place to get a sense of the systematics. I also wanted to point out there are mixed signal special structures that you have to put in place to make sure that you can actually look at the circuit to process marginality. And I'm not going to get a chance to talk about it today. There are concepts of figure of merit circuit, very specific kinds of circuits that can pick out that circuit marginality, which can go into the mixed signal portions. Continuing on, here was a case where we are looking at the systematic yield loss elimination by using those kinds of characterization structures. Here was the target D0 across time. You can see that if you just look at pure contamination or the random defectivity, this fab's well below where the target is. Problems, the red curve. And you can see that there had to be metal fixes which had to be put in place. This is not making sure that you remove dirt. This is making sure that you don't have process design interactions. Had to change, photo etch, etc. Process optimization on the via, we talked about the via. ILD optimization, which I talked about earlier a little bit. And then going back and cross-optimizing all those three together. Because you could really do something to your metal process optimization which can totally destroy your via. For example, you can make sure your metal lines are great by doing a beautiful OPC, but you have a process where the taper is so large that the via falls off the top of the metal. Got to co-optimize them together. You can change your ILD and totally mess up your via edge. You might get open vias, high fail rates. So you can see what has happened is the characterization monitors have been able to pick this up early and drive this down toward the target D0. And this is what the characterization monitors and doing the yield modeling that I'm talking about, looking at the process design interaction lets you do. I don't want to say that everything happens before you send the process into production. A lot of it does happen during the production. I'm just going to touch on it very simply here, saying there are two kinds of things that go on when you are in production. One is just essential baseline improvement. This is where your inspection tools, what kind of scribe line structures, what kind of monitoring, and what frequency you monitor at to get statistical validity does really matter. Second thing is excursion control. And you heard about that today a little bit. Here is where your APC, understanding very quickly, getting feedback almost in line before you end your chip, before you end your product after many, many months. You figured this out from inline inspection and make sure you understand the root cause and not let these excursions happen. Because when you're in full production, this is also a killer. So there's a lot of work that goes on during production. I don't mean to belittle that, so I wanted to put this foil to you, that there is a lot of work, but we're not going to touch this today too much. We're going to touch about the early part, the pre-production part that governs the ramp. Okay, so I'm going to jump in and talk a little bit about the parametric yield loss, because I've kept to more or less function when I talk about via fails, etc. Talked about functional bit, not to talk about the parametric portion a little bit. Again, going back to the same foil, here is the huge difference in the parametric between the real product and what you saw in the SRAM. Okay. So why do we get parametric failures, or why is it a big issue? Because process variation is a major source of yield loss, especially in system on a chip, because you have different kinds of designs. You have SRAMs, you have analog portions, etc. And the analog and the mixed signal components are especially sensitive to the process variation. I'll talk about that a little more. And we also find out that the analysis of doing parametric yield is much harder than the ones that I talked about, because of simple things, that you have huge interaction between design and process, some of which come from phenomena like mismatch, noise, and just some layout interactions. It's much harder to do layout for the mixed signal chips. Those of you that are involved in this know this already. The second thing is that you need very, very accurate models. Because it's so sensitive here, you need extremely accurate model to be able to analyze the situation and simulate the yield loss. What are the design for manufacturing challenges? And I roll the device for manufacturing part into parametric problems because you have to do a bunch of design changes often in order to make sure that it matches with your process or centers with your process. Simple things, that even having a couple of angstroms difference in your gate oxide is enough to make a 10% variation. Your L gates have become very, very small. That means any variation in your litho or etch is a huge percent variation to your gate length. Essentially, you can see that as you scale down, if your variability does not scale down with it, then it becomes a large percentage of the change that it does to your nominal structure. System on a chip designs are especially susceptible to this process variation. For a 1.8 volt DAC, you need 1.8 millivolt difference, so in order for you to resolve. This is huge. If you think about what we said about the TOX or the L gate here, this is really hard to achieve. I also talked earlier on, SRAMs are showing more and more analog-like behavior. Simply using the digital worst case corners, etc. is not good enough for design because you do a lot of tricks in layout and the performance is a big issue in SRAM. So it's behaving more and more like an analog component rather than a pure digital component. And the final thing is that deep submicron chips or deep submicron products and designs are extremely sensitive to the intra-die variation. In fact, the intra-die variation which I talked about for the ILD, for most cases, swamp any other kinds of variation that you talk about unless you have really bad control in your fab. For a reasonably controlled fab, this is the variation that kills you. This is a busy foil. All I want to show here is that the solution to the parametric is somewhat similar to the solution that I talked about for the functional yield. You need to do characterization and you need to understand your product design really well. Here the characterization is not talking about parts per billion fail or defectivity, it's in terms of a statistical SPICE model. All of you know that the SPICE model is the designer's definition of a device. One can simulate the product and the design if one understands the SPICE model. What you need to do is inbuild in your SPICE model the statistics or the variations that you are seeing due to the fab. That's what makes it possible for you to get the process design interaction for the parametrics. Once you're able to do the characterization and get the attributes from your design, you can now do design for yield. You can do design for manufacture or design for yield, where you can change the designs. For example, simple things that are done are resizing of the device, making sure that your mismatch is lower. We'll talk about that a little bit. Second thing you can do is you can do a little more accurate modeling. Instead of using the worst case corners that are used for digital, which are not very good for analog, you need application specific corners which relate to both your technology and the product that you're going to run. That is really, really key to making sure that you can do the trade-off between performance and manufacturability. The honest truth is there is a trade-off between these two. If you want the highest performance, you push your design, you're not going to be great in manufacturability. Problem is, where is the sweet spot between these two? Has to be gotten by doing some really good modeling and then using this statistical SPICE model to run your product design. I want to touch very briefly, and we are not going to go into this today, but just to give you a flavor, one of the important things that you need to do in order to make sure you have a good idea of where your statistical SPICE model is going is to have test structures which are appropriate that can let you track if you are getting variation in your statistical SPICE model. Is your variation changing over time? Is the fab no longer centered or the process no longer centered where it's supposed to be? Has the device deviated? If you think of high-speed silicon germanium, this is a real issue. Because what you can observe in the scribe line has to correlate really, really well with the transistors that you're seeing at high speed. That makes it really difficult, but a critical portion where how do you manufacture and test those scribe line structures? How do you design them to make sure you know how to update your statistical spice models with mismatch with the variations that you're seeing? And that is very, very key for the parametric portions also. Takes a little long to come up, but I just want to touch briefly on the statistical front-end modeling. Normally you have spice models that many of you have seen which define the device or the nominal case of the golden die. What you also get is the variability that you see in your device. What you need to do in order to be simulating the parametric yield or the parametric yield loss is making sure that you get the global correlation correct, that is the correlation within the device parameters correct. You need to make sure that you have got a good understanding of the mismatch or the intra-die variations. And if you can get these two, you have application specific corners. That is not the 3 sigma or 6 sigma corners in the X and Y direction, but really application specific corners. This is what your designer needs to design to. Otherwise, you're going to either over design or you're going to make it really, really sensitive to your process. So those are essentially the key parameters that you need to model accurately in your statistical spice. So this is a key aspect of it. I'll talk very briefly on mismatch, and I'm jumping through a couple of foils, and before I jump through, I should say that in order to get your statistical spice model correct, especially if you're interested in pre-silicon spice models, it's very important for you to be able to do a good set of device simulations, what we call technology CAD simulations, TCAD simulations. You must have them accurate. You also must have reasonable amount of data to fit on top of the TCAD simulation so that you can derive those statistical spice models. I will touch on one aspect of it, the mismatch. The first order models are what we call corner simulations. It tells you what is the worst case difference between two transistors which are mismatched with a certain size and a certain distance away. This was fairly useful about a decade back, but as we progress through, we find that this is no longer valuable. You really need to understand the distribution of devices that you get. So the first thing that happened is new device models came up that can take into account this mismatch. These models, I'm not going to go into, they are called EKV models. That is slightly different from the normal MOS models that we use, where we are able to account for this mismatch a little bit better. And the final thing that we are doing right now is we are looking at defining several layers of variation. Variation that is intra-die, of which mismatch is a portion. Variation within wafer, wafer to wafer, etc. Getting that is really, really important to managing the complexity of the design. Because if you can get this accurately, you are able to simulate your design using Monte Carlo type simulations and figure out how your design is going to behave with respect to certain things. One of the key aspects of this is to make sure that you do not overcomplicate the problem by making the problem thousands of dimensions. One of the things that we find nowadays to be useful is doing a complexity reduction. That is not only doing a statistical spice model, but doing a reduced order statistical spice model which takes into account all the key components of variability and the key correlations, but not use it in the full simulation. Use only the important portions that you need. Here is an example for a current steering DAC, where if you did not use the mismatch and if you did not use the statistical spice models, you are well within the spec. The moment you added the mismatch, you could see what's happening in reality. The interesting thing is, here is the yield curve for it. It says that without the mismatch, you would have gotten the red, and with the mismatch, you're now seeing the green. So it's really important. The reason I put this example up is it's key to making sure you understand the mismatch and the intra-die variation in your models so that you can get the parametric yield correctly done. The next step obviously is to resize your devices to see if you can do any better. Here is the case that I was talking about where you are looking at the trade-off in performance versus area. I talked about performance versus manufacturability. This is performance versus area. The important thing here is to make sure that is as you go up in the area, you can see that you get further and further improvement in yield. But this kind of simulation allows you to say that, okay, if I go above 5, it's not very useful. It's diminishing returns, essentially. So doing this kind of simulation becomes really important in figuring out how far you should go, and at least how far should you go, and beyond which it's not very useful to get any performance gain, essentially. You're not going to see any yield gains. I'm sorry, the reverse. You can see you cannot see much yield gain out of that performance. This is the case of the same current steering DAC. We're able to improve the size of the devices and get a much better yield. This is a foil that you don't have. I just wanted to wrap up this section by saying that we've talked about essentially functional and parametric yields. We've talked about characterization monitors, doing modeling and characterizing the process real well with respect to features. We also talked about what is the statistic or the features that you have on your design, really. From this, you can get the functional and parametric yield. You can do analysis based on these yield predictions, and then finally go back into optimization. Okay? Talk briefly about the optimization of process as well as design in order to be able to get to the yield numbers. I'd like to touch a little bit on the design for yield aspects that I have not touched on so far. So if you look for design for yield, which Jack mentioned in the morning, there are many ways you can do this, and you can do that in many places. For example, you can do pre-tape out IP optimization. Your footprint is not fixed, your product is not fixed, you can actually play with it by doing early simulation. This is why you need the early process design characterization. You can also do it at post tape out. That is, even if the product has been taped out, you can make changes. For example, doing things like via overplots, or changing a line size, or changing some of the routing, could be changing some things like Salicide that I talked about, widening the lines. You could do this as long as you did not change the footprint. This is also done. OPC or PPC is actually one of the great things that you can do here. You can actually do MDP and OPC in order to get yield improvement. It's just not a simple matter of getting better printability. It can be used as a design for yield tool. Important thing here is you need to manage the trade-off between the yield gains and the area and performance. Because you're at a very early stage, you could do the totally wrong thing and be in the diminishing return space where you're doing a lot of work but you're not getting the yield benefit. So having this trade-off is key for that. You could look at migration where you're taking a product from one fab to another. Here you need to do design centering. You want to make sure that you get back the yield that you got. See, Bruce talked about a little bit in the morning about copy exactly, which is a great way to go. But if you don't have that, you need to go back and make sure that when you transition your product from one fab to another, you are centered on the process design. And again, you need to use design centering process or design for manufacturing processes to manage the performance and yield. And finally, we talked a little bit in the VIA, but here's a general case where you do a product-driven device optimization. How should you optimize your device? Is it great to have the largest drive current, least leakage? Is it a low power part, low noise part, etc.? You look at your product and then from that drive your device optimization. These are early things that you need to do essentially for the component that I call designing for yield. One of the important concepts that I've been touching on and haven't talked about is getting a great design kit for manufacturability. Early on when you generate your process, you can generate a design kit which contains things like design rules, the statistical spice models that we have been talking about, extended rules. Having one of these early on can make the designer's life much simpler and the design for yield really, really important. These are some just examples of the design for yield activities that are going on right now. For example, routing and full chip optimization is one of the things that goes on. Of course, this is done in the pre-tape out phase. Talking about memory optimization again, such as changing the bit cell or changing the redundancy, for example. We have done several simulations where you look at what redundancy scheme you should have and what you have and how beneficial those are, for example. Look at parametric and analog that I talked about, design centering. One of the key things that we've been looking at is the cell library optimization. If you go back to the number of vias or the number of contacts that I talked about, One of the things that standard cells does for you is many of them are used in the product itself. So if you can look at a standard cell which is used fairly often and can optimize it so that it yields well, you can get a huge boost in your yield. So that's the other thing that we do. And here are some simple examples that I talked about already, doubling contacts and vias via over plots, metal extensions that you can do. Just get some standard cell improvement. And key to doing design for yield is again characterizing the yield and performance accurately and reducing the impact of systematics, that is the process design marginality, but now in the parametric and functional sense together. With that, I'm coming close to the end of the talk, so I'm going to talk a little bit for reliability loss and designing for reliability. And since Kobayashi-san has actually done a good job of talking about the reliability portion, I'm going to go through it fairly fast till I come about the design for reliability component, and then we can have questions and answers. Just like I talked about the yield gap or the systematic portion, that is the feature-based yield loss, it's the same kind of graph shown for what you can get if you optimize for reliability versus the unoptimized version. That is, if you just extrapolated back through technology, your reliability curve should have been something like green. What you're actually seeing is red if you don't do the right things. The important thing here is, in order to manage the reliability gap, you have to do the same kinds of things. Characterization of the reliability fail modes, what kind of reliability fails you are getting, get as physically based as possible in modeling reliability, and then doing application-specific design for reliability. And this will become obvious when I talk about the fact that how do you generate a reliability spec. So first, the device-related reliabilities, which has to do with gate oxide integrity, hot carrier injection, and NVTI. And NVTI, of course, is a very, very big issue right now. And for the new generations that are coming out, this is a huge train wreck for us. Then we have the interconnect-related reliability, which has to do with electromigration and stress migration. And then I'm going to go back into how you optimize for that, similar to what I talked about for the yield. Skipping one foil. If you look at gate oxide scaling, there are many components which cause reliability loss. First of all, direct tunneling through the gate. Talk about hot carrier here. NVTI, which has temperature and bias-based instability in the oxide interface. And then for very thin oxides, you also get mobility reduction due to Coulombic interactions. I'm going to not talk about the top and the bottom part today. I'll just briefly touch on these two components which have to do with hot carrier as well as the NVTI. Again, I'm not going to go into the basics of the hot carrier reliability, but what is interesting here in this graph is that Morifuji had presented in VLSI 2000 that the PMOS hot carrier degradation is not only a matter of electric field, surface states, but also degrades due to the impact of physical stress. In fact, he talks about here about the different lifetimes with respect to the different amount of stress that he's seeing. So what has become important for hot carrier right now is that not only do we need to manage the fields and the current densities, you also have to manage the physical stress in the next few generations of CMOS. I'm going to leave the hot carrier as such now because I think you have tremendous expertise in this room. No point in pushing this any further. If you look at NVTI, essentially what you're seeing is due to negative bias and temperature, you're seeing increased threshold voltage, decrease of mobility. And this is true. This is a very, very big problem in the PMOS FETs today. What makes it really difficult is that NVTI is extremely sensitive to the process conditions that you've already seen. So you see more, and NVTI becomes progressively more severe as you reduce the gate oxide. And it is the most serious reliability problem that we are seeing today in the front end. If you look at these two graphs, one of which Kobayashi-san presented, it shows two things. Sure, it scales with the gate oxide, but it also scales with the amount of water content that goes into the gate oxidation process itself. What I'm trying to point out here is that there are different process parameters that impact the NVTI that you cannot measure through a device parameter itself. For example, if you just measured the oxide thickness and predicted the NVTI, it wouldn't do. You needed to know under what condition the oxidation was exactly done in order for you to be able to predict the NVTI. This is why it's so very serious. There's very little known about the physics and chemistry of NBTI, and by that I don't mean there is very little known really. What I really mean is that there's very little agreed upon on the physics and chemistry. There have been papers on it, some of the aspects of it is known, but we are finding out more and more that it is not really clearly understood. There's no practical NBTI model that we have found that can be used physically in order to predict, like we are predicting parametrics or systematics. And therefore, there are no clear design rules. There are some process rules which you put in place, but they're not comprehensive enough. There is a strong dependence on the process conditions, and the mechanisms remain somewhat unknown. And some trends for process conditions we have found have also been contradictory, depending on what fab we have looked at. So this really makes NBTI designing for NBTI or designing against NBTI really difficult. Final thing is that the NBTI impact on the circuit is really circuit dependent. It's just not purely a matter of looking at the device. So what we did to address this problem is essentially borrowed a page from what we had done for the parametric simulation. If you think of the statistical SPICE model, we are talking about variability does not change across time. We are talking about a static variability. I talked about monitoring the SPICE model through appropriate test structures so that you can update your SPICE model. This is the case where we look at the degradation due to the reliability of the SPICE model itself. Now you can go back to the techniques that you have used for your parametric design for manufacturability or designing for yield, go back and do the same kind of thing for design for reliability. Essentially what you have done is you have put together not only a SPICE model that has variation associated with it due to wafer, die, etc. You're looking at the degradation of that variation over time so that you can model how your circuit is going to behave. So that's a key component. Again, I will skip through the electromigration concepts pretty quickly. Suffice it to say that due to the electron wind, the electromigration that you get leads to essentially getting resistive opens for you. You need not constantly get a complete open. What you'll see is over time your resistance increases. Now if you go back and think about what we said about the parametric portion, if your resistance increases over time for these lines, it's going to be a huge issue for your parametric. Your parametrics are going to fail. And this can even happen for copper. I'm showing the aluminum part. In copper, for example, when you see these kinds of electromigration for lines which connect contacts, for example, you even start seeing functional fails. So this concept of seeing time varying change of resistance is a huge issue to the parametric as well as to the functional yield. Again, this graph is something that Kobayashi-san did explain, where he talked about the fact that as we moved from aluminum to copper, things got better. In fact, they got about 100x better. But there has also been some trouble, as you already know. If you look at copper-specific electromigration, it's really important to look at the barrier layers as the barrier layer is thinning down. One of the key aspects is that if the barrier layer thins down and does not coat really well, you can get copper diffusion in from the contactor via, essentially. And this is a huge issue. The other issue, as had been pointed earlier, is that you can see the diffusivity difference and the addition or the wetting between the barrier layer and the top surface can be focal points where you get electromigration-oriented voids. This is a case where you're looking at different barriers and different times. Essentially, with respect to the barrier, you can see that the barrier layer has a huge impact on the electromigration that you're seeing for copper. Next important thing is obviously stress migration. Again, I'm not going to spend a whole lot of time on it. Important to remember here is that you have to do a decent amount of anneal and a reasonable amount of anneal before you put your dielectric down. In fact, we're talking about essentially doing elevated temperature dual Damascene process in order to make sure that you do not create these voids after you put the dielectric and go to high temperature steps later on. Important thing here also is the fact that Kobayashi-san showed that the VI etching or the formation of the VI itself is a big issue in stress migration and stress effects that you see and the failures that come out of that. Here is a good example of where you're looking at the impact of barrier layer itself and the effect of VIH. VIH is a huge issue. You could sputter the copper out from the bottom and create voids automatically. So optimizing not only the layer that you're talking about, but optimizing the edges of the via that come after that is a key issue for stress migration itself. So what do we do? The important thing is that till now we have been looking at reliability in this small circle. We assess the reliability, we measure it, we know how to measure the test structures, we go back into the device and process and then design to increase the reliability or improve the reliability. One of the key things we find is the fact that the impact of this reliability that we are measuring is different for different circuits and products that you use. So we formed an outer loop which talks about assessing from the device degradation models that I talked about earlier, but the same kinds of things for stress migration, electromigration in the interconnect, that you actually do a circuit simulation and find out application-specific reliability targets. First, let us figure out what the spec is before we start improving. So this is the outer loop is a key component for making sure you have application-specific reliability rules, and then use these in the inner circle to do changes in your process and design to optimize the reliability. That becomes a key methodology for designing for reliability. I'm going to summarize here with an yield ramp and sort of culmination of all the things that we have talked about. What we find is that if you look at the Berkeley study on yield ramps, for example, you'll find that the yield ramp correlates pretty well with the initial yield condition at production. In fact, what we find is what I've been saying a little bit earlier, that is the race is really over by qualification. If you have not taken care of yield and reliability early on and started with a decent yield in the beginning, you're not going to ramp up well. So these are some of the benchmark ramp rates that have been seen, and again you can see the correlation. I also wanted to point out back again that inspection and yield optimization during production does account for the last 10%. Let's not worry about the exact number 10%, but there is a significant yield improvement to be done even at production itself. So finally, what does it all mean in terms of dollars for us? If you look at the top 95th percentile people who can do good yield ramps versus the top quartile, you can essentially see a 2x difference in cost or profitability, however you look at it. And if you're behind the curve in the bottom, you're talking about losing the market window and therefore having huge losses. So essentially, once again, the aim of my talk is to say, while this is the last talk, you need to take care of the yield and reliability portion up front before you get into the production itself. And while you're thinking about the new processes and the new designs, think of the interaction that goes on between the design and process so that you don't end up somewhere out here. Thank you.